Another application of the derivative is called time rates. Okay, so this is one of the obvious application, because as we all know, derivative is already considered a rate of change. Okay, so let's say we have two variables, one is dependent and the other one is independent, and it is let's say in this form, y is equal to a function of x, then therefore its derivative is derivative of y with respect to x, or the change of y with respect to x. So let's say time is our independent variable. Let's say time would be an independent variable. Then therefore, whatever is the function, if we get the derivative, then it would be a change with respect to time, and therefore the topic of time rates. Okay, so let's answer some example problems here. Let's say a man crosses a footbridge at a rate of 5 feet per second. So we have here a man. So the man is on a bridge. Okay, just pardon my drawing. And he is walking. He is walking the bridge at a rate of 5 feet per second. Okay, now directly beneath him, a car passes by. When a car directly beneath him passes by at a rate of 10 feet per second. Now, of course, this footbridge, sabi dun sa problem, if the footbridge is 30 feet above the ground, so let's draw that. So we have here a car. Okay, let's say ito yung car natin. And it is traveling at 10 feet per second. Okay, so, and the car and the man is initially 30 foot apart. So 30 feet apart. So how fast are the man and the car separating after 2 seconds? So let's try to simplify first. Let's try to simplify our drawing here. So let's say that this point is the man, and this would be the length that he would travel at a certain time. He is walking at a rate of 5 feet per second. So therefore, let's say that length is 5t. Okay, now whatever is the time, now let's say that this is 30 feet per second, 30 feet. Let's say that is 30 feet, the height of the footbridge. And we now have here another length, which is the length represented by the movement of the car. Okay, so the car is moving at 10 feet per second. So let's say that this is 10t. Okay, so the problem happens exactly at this point. Okay, so therefore t is the time afterwards. So exactly at this point. So if we are going to draw this, essentially it will look like a box. Okay, so okay, this would now be like this, diba? It would look like a box. Something like that. Okay, so the car is here, the man would be here after a certain time. So we are investigating after 2 seconds, and the rate at which they are separating would be represented by this line. Okay, so whatever is that, the length of that line, or try to imagine that the man still would still go forward, and the car here would still go forward in this direction. Okay, so both of them are moving and are going forward. So therefore, the red line will continue to change. Okay, the red line will continue to change, and it will be the representation of their separation from each other. So the question is, what would be the change of this separation? Okay, so geometrically, this point, no, from this point to this point can be solved using a distance formula, which would be in 3 direction, and it will be equal to, so let's say that this is S. Okay, S would be equal to the square root of 5t squared plus 30 squared plus 10t squared. Okay, that would be the equation defining S at any time t. Okay, so this actually came from, if you remember our distance formula, if you remember, this would actually be x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared, and then plus z sub 2 minus z sub 1. Okay, that would come from that formula. Well, we just use here in terms of t. Okay, so let's continue to solve. So therefore, this will now be 25t squared plus 900 plus 100t squared. So S will be equal to 125t squared plus 900. Now, ito yung sinasabi ko kanina. This is what I'm talking about a while ago, that we have a function S as a function of t, wherein this t here is your independent variable. Now, if we get the derivative of S with respect to t, then therefore we are now solving the separation between the man and the car at any time. Okay, so let's get the derivative of that. So we have 1/2 125t squared plus 900, then this will be raised to negative 1/2 times 250t. Okay, 250t. So ito 250 divided by 2, this is simply 125. So 125t divided by the square root of 125t squared plus 900. This is now my derivative of S with respect to t, which represents the separation of the man and the car at any time t. So in the problem, you are asked to find how fast are they separating after 2 seconds. Okay, after 2 seconds. So when t is equal to 2 seconds, derivative of S with respect to t, which is the change, the change of their distance together, their separation. So this will be 125 times 2 divided by 125. This will now be times 4 plus 900. So let's go ahead and get our calculator. Okay, so we have 250 in the 250 of course in the numerator, and divide that by 125 times 4 plus 900. Okay, then let's get the square root of our denominator. Then let's press equals, and the answer is 6.68. So the derivative of S with respect to t is equal to 6.68 feet per second. Okay, so that is one example wherein we were able to obtain a function which has time as its independent variable. Now, what about if that is not possible? So, let's say here in our problem number 2, this is the more, actually this is the more frequent example wherein you cannot have t as your independent variable. Rather, you would have to get the derivative with respect to time. So let me just write it down. You have to get the derivative, or you have to differentiate the function with respect to time. Okay, so let's say here a ladder 20 feet long is leaning against a vertical wall. So we have a wall and we have a ladder. So our ladder is 20 feet long. Now if the top of the ladder, the top slides downward at a rate of 2 feet per second. So we already have a rate here, 2 feet per second. Okay? Find how fast the lower end is moving when it is 16 feet from the wall. Okay? So find how fast this lower end. So this lower end, the lower end of the ladder, this is moving, and we want to find out how fast is it moving if this is dropping at a rate of 2 feet per second. So let's say this is x. Okay, now let's say this is y. Okay, the length of that is y. So therefore, the derivative of y, or the change of y with respect to time, would be equal to negative 2 feet per second. Now, negative is a sign because it is the y is decreasing in length. So therefore, that is negative. If y is increasing in length, then that would be assigned a positive value. Okay? So we have here a derivative with respect to time. Now, what we want to find out is the derivative of x with respect to t. Okay, sabi dito, find how fast the lower end is moving when x is equal to 16. Okay? When x is equal to 16 feet. So, the main governing equation here, as you can see, would be a right triangle, and we will utilize a familiar equation, which is the Pythagorean theorem, wherein x squared or y squared plus x squared is equal to 20 squared. Okay? So, we will have to get the derivative from that equation. So, let's go to our next page. So, we have x squared plus y squared is equal to 20 squared, which is 400. So, that is our main equation. So, we will now get the derivative of each variable with respect to time. Ito yung sinasabi ko. We have to get the derivative with respect to time because we cannot create an equation which has time as its independent variable. So, derivative of x squared will now be 2x. The derivative of x applying chain rule will now be derivative of x with respect to t. Okay, and then 2y, and then derivative of y with respect to t. Again, applying chain rule. So, this will now be equal to 0. What we want to solve here is the derivative of x with respect to t. Okay, so 2x, this will be 2y dy with respect to t. Transpose to the other side. We can cancel out 2. And finally, derivative of x with respect to t will now be equal to y over x times derivative of y with respect to t. Okay? Now, we want to solve the derivative of x with respect to t, which is the change of x, no? The change of the movement of the lower side of the ladder when x is equal to 16. So, at this particular point, when x is equal to 16. Now, when x is equal to 16, based on this Pythagorean formula, if x is equal to 16, therefore, y would now be equal to 400 minus x squared. And 400 minus 16 squared. So let's get our calculator. 400 minus 16 squared. So 144, we know that the square root of 144 is 12. Okay? So we go back here to our formula for the derivative of x with respect to t. So derivative of x with respect to t is equal to negative y over x. So negative 12 over 16 times the derivative of y with respect to t, which is the change of the top side of the ladder. So that is negative 2. So this will be positive 24 over 16, or that would now be, so we both divide it by 8, so 3 halves. Okay, 3 feet per second. Okay, so if you are confused with the unit, no, just a clarification, 2 here, the unit of 2 is feet per second. Okay, this is in feet and this is also in feet, so therefore both of them would cancel out and the final unit would be in feet per second. Okay, so the movement or the change of the lower end, that's how fast this lower end is moving to this direction. 3.5 or 1.5 feet per second. Okay, last problem. Let's say a kite is 40 feet high with a cord with 50 foot or 50 feet of cord out. If the kite moves horizontally at 5 miles per hour directly away from the boy flying it, how fast is the cord being rolled out? Okay, so we have a boy, sabi, meron tayong bata. Papalipad siya ng saranggola, is flying a kite, no? And the total amount of cord that is rolled out at the moment is 50, and the height of his kite, okay, is, let's say, 40 feet high. Okay, so let's just assume that this particular distance is this particular length is already negligible. Okay, so next situation here from the problem, there's a wind blowing directly away from the boy and it is moving horizontally at 5 miles per hour. So this is moving 5 miles per hour. So if I may illustrate the change here, your kite will still be at 40 feet. Okay, your kite will still be at 40. The boy's kite will still be at 40 feet. But since it is moving horizontally, then therefore the 50-foot line would be longer. Okay, so let's say this is situation 1 and then situation 2. After a certain time, because the wind is blowing away from the boy. Okay, so therefore there is a change of the length of the cord. So yun yung tanong dito, that's the question. How fast is the cord being rolled out? Okay, so let's say this is x. How fast is this cord being rolled out? So we want to get the derivative of x with respect to t. And if you can imagine, we will again deal with a right triangle. We will again deal with a right triangle. This is x. This is the one that's changing. 40 feet would be constant because that's the height of the kite. That's the constant height of the kite. And let's say that this is L. Okay, the horizontal distance from the boy to the kite. Okay, and from this, the equation that we can derive from is again using the Pythagorean theorem, because this is a right triangle. We have x squared is equal to 40 squared plus L squared. So if we are to get the derivative with respect to time again, we have 2x derivative of x with respect to t this one is a constant, so that is 0, is equal to 2L times derivative of L with respect to t. Now, the x would, or 2 would cancel out, and the derivative of x with respect to t would be L over x multiplied by the derivative of L with respect to t. Okay? So, we already have the derivative of L with respect to t. Okay? This is the derivative of L with respect to t. That's how fast the kite is moving away from the ball. So, from the boy. 5 miles per hour. Now, what you want to find out is what is L and X. Okay? So, L and X would be solved. So, let's use the first condition. The initial condition is that this is 50 feet. This is 40 feet. What is L? Okay? Kasi ito yung this is the first condition where the wind blew. So, pinapahalap lang sa atin, when the wind blew 5 miles per hour, how fast would the line or the cord be rolled out? Okay? So, at this particular point only. So, L will now be equal to the square root of 50 squared minus 40 squared. So, if we will get our calculator, we have 50 squared minus 40 squared. 1,600, so 900, and square root of that is equal to 30. So L is equal to 30. So let's go back to our derivative of x with respect to t. So L is equal to 30, x is equal to 50, and our change of L is equal to 5 miles per hour. Okay, so this is feet, this is feet. Both of them will cancel out, and our unit will be in miles per hour. So 50 divided by 5 is of course 10, and 10 divided by 30 is 3. So the derivative of x with respect to t is equal to 3 miles per hour. Okay, so I hope you learned something from this short video regarding time rates. Just remember that there are two cases for time rates. One case is you have a function. Let's say you have a function of a length, and it is with respect. It is length as a function of time, So if we are to get the derivative of L with respect to t, because t is your independent variable, then this would be the change in length with respect to time, which is similar to speed, So that is the concept of time rates. Now, there are certain cases wherein, this is case 1, there are certain cases wherein we cannot simply get this type of function. Then whatever is our function, we simply have to differentiate. We simply have to differentiate our given function with respect to time. Okay, so those are the two cases for time rates.